Okay. Good morning, everybody. Happy Thursday.
Morning.
Morning. All right, folks. So today, exciting first day of Unit 2. Good news is Unit 2 is actually pretty short. Unit 1 was a little longer. So I think we're going to be done with this in probably 2 weeks
Mm,
instead of like 2.5 or 3 weeks. So today's our first day. Now, I just want to give you a warning. Today's lesson is a lot of definitions and vocabulary. But I thought it'd be good to just get this out of the way in the beginning. It'll give us hopefully a strong foundation for like using these ideas in the later lessons next week. So, lesson one here for Unit 2 called graphing relations. Graphing relations. Get out your paper and your pencil. I am going to ask to see everyone's notes today at the end of class to mark you down for participation. Since I can't see what you're doing on your cameras, I want to see your notes. So at least I know that you've been trying to follow along and have these down on paper so you can use them later. I want you to use your notes on quizzes or homeworks or tests. So I'll give you a second to get ready. If you haven't already, get your paper and your pencil. Here's our objectives for today. We're going to define relation. What is this? Then define independent and dependent variables. And we have to define domain and range. And there's one I forgot to put on here, but we're going to do it today. Define continuous and discrete. The continuous and discrete relations. Math relations. So this is what I meant by it's kind of a lot of vocab, a lot of definitions today. And we're also going to be graphing, hence the name, right? Graphing relations. So we'll also be graphing relations. So that's where we're headed. Any questions or concerns before we get started? Okay. Make sure you're taking notes. If you want me to slow down, if you want me to go over something again, turn on your mic, let me know. I'm more than happy to do it. And for some of these pages that you'll see, it's okay if you want to take pictures of it, but I still want you to copy down definitions and any work that we do. But if sometimes I'll have graphs up and you don't have to copy all that down. If it's too much, just take a picture of it so you can look at it later. So I want to start our talk about relations and all these other terms today with an example. So here's our example one. And we're going to use this to define most of our stuff today. So here's our first scenario. Brianna is excited because she has just been hired by a family to babysit on Saturdays. Okay, the family will pay her $12 per hour for a maximum of 8 hours. Maximum means the most. So means that she won't be working for 9 hours and she won't be working for 10 hours, but she could work anything less than 8 hours. She could work one all the way up to 8 hours. Make a table that shows her earnings for different numbers of hours. So here's our task. Make a table that shows earnings, meaning how much money she's made for different numbers of hours. And it doesn't tell us what numbers of hours. So let's just start with one and move up and see what this table might look like. number of hours and that will correlate or correspond to her earnings, her money made. Dollars per hour. So let's say she works 1 hour. How much money should she make if she only works for 1 hour? Can anyone help me out with this? What do you think? Based on what we're seeing in the scenario, in the word problem.
Right?
Sorry, I covered you. What was that?
Sorry, $12?
$12. Thanks, Tira. And help me out with another one, I guess. How about 2 hours? Let's say she goes in and she works for 2 hours. What do you think she'll make for 2 hours?
$24.
Lauren, high five. There's a pattern here. If we worked for 3 hours, it's going to be another 12, 36. And we could go all the way up to 8. It told us in the story this time that there's a maximum. That doesn't always happen, but in this case it did. It's basically telling us we can work all the way up to 8. So in my table, that'll be the biggest number we see. Okay, kind of ran out of room here. 7 and 8. Maybe I should have done it higher up. And to skip around, we could multiply 12 times the number of hours. Let's try that. 8 times 12 is 96. Let me test that theory out. Try multiplying 12 by number of hours for one of the lower ones that we've already done. 12 times 3 is 36. That worked. 12 times 2 is 24. That worked. So let's fill in the rest of the table using that shortcut. 4 times 12, $48. And 5 times 12 is 60. 72. And 7 times 12 is $84. All right. Apologize for the running out of room there, but there's all the different hours that she could work and the possible money she makes. All right, so we made a table.
Josiah,
Yes.
do we write this down?
Yes, please write this down.
Okay.
Hey, I got a question for you guys. I'm not sure if this is viewable from your perspective or not. Do you see this giant, like, dark bar in the middle with my menu options on it? Or is it just me? Right in the center of the screen?
No, I don't see it.
Okay, so when I'm sharing, I see it, but you guys don't. Okay, I think it's probably going to be in the video, though. Okay. Thank you. So there's our table. Now, we haven't really defined anything yet, but we were able to correlate the number of hours she works to the money she makes. Okay, I'm going to move on, but we're going to stick with this example for a while. So copy down this table if you haven't already. And if you can't see it or if you need to have a question on it, let me know. I'll wait for maybe 15 seconds and then we're going to move on and start defining some different terms.
Josiah, I can't read what it says after 6.
Okay.
For isn't it 7 and 8?
It's 7 and 8. Yeah, let me so for 7 we have $84 made, and for 8 we have 96 made.
Okay, thank you.
Yeah. Same table here, but I'm just going to have the bottom showed better. 6 hours, $72 earnings. 7 hours is 84, and then 8 hours is 96. And we'll stop there because it says in our story that there's a maximum of 8 hours, kind of a cap. Okay, I'm going to move on. This story is an example of a relation. When we say relation in math, what we mean is a relationship between two sets of quantities. Or variables. Remember, a variable in math, what we mean by that is just a number that we don't know the value for yet. So we usually write them as x's or y's or a's, b's, c's, some letter. But we're relating one type of variable to another. In our story about Brianna, the two quantities or two variables that we're relating together would be what? Hours worked and money made. Hours worked and money made are our two variables or quantities that we're relating together.
Morning, teacher.
Morning, Philman.
How are you?
Good. How are you?
Good, good.
So that's all a relation really means, is some relationship between two different quantities. Remember, quantities means numbers. So both of those different items are expressed in numbers, right? Dollars and hours, basically. Hours worked, dollars made. Now, I also want to define independent and dependent variables. So far we've talked about relating two different variables together. We saw making a table with those two variables. But now we want to talk about, well, what types of variables? So every time we have a relation in a set of two quantities, one is always dependent on the other. One depends on the other. So that means one is dependent, or I'm sorry, one is independent. One acts on its own first, kind of, and the other one follows it. Yeah, a lot of people showing up now. What's going on? Okay. One is dependent of the other. One is independent, and the other is dependent. So I want you to think of independent as the one that comes first, the variable that happens first. And then the dependent one follows whatever the independent one is, happens second. So take a minute and keep copying this down. And then I want to ask a question. So let's now look back again at the story of Brianna and her babysitting for a certain number of hours and making money. Our two variables are the money made and the hours worked. Which one do you think is the independent? Which one of those is happening first? The money making or the hours worked? Any thoughts? Which one's first? Which one's second? Which one's independent? Which one's dependent?
Wait, what was your question?
Okay, sorry. The question is, out of our two variables in the story of Brianna here, which one of these seems like it's happening first, and which one is following that?
I
Is-
think it's the 12 per hour first.
So does she makes her money and then she does the work, or does she do the work and then make the money?
Oh no, she does the work and then makes the money.
Very good,
So-
and very good. Thank you. I guess I was asking it in a kind of a strange way. Think about when you were trying to figure out which variable is independent, which one's dependent. Think to yourself, which one of these happens first? Are you doing the work and then getting the money, or backwards, vice versa? Thank you, Tira, for helping me out with that. So in our table, let me change my color here. In our table, it's customary to always put the independent first. So I'm going to label that here, independent. And then earnings, her money per hour, that was dependent. Because the money she makes is dependent on how much time she worked, right? So we have to know her hours worked to figure out her earnings. Any questions or comments so far? Please. Okay, back to this. So whenever we're dealing with a relation and we're trying to make a table of it, or later we'll make a graph of it, then I want you to think to yourself, which one's dependent, which one's independent, which one happens first, and which one happens second or follows the first one. Which one do you need to happen first for the story to make sense? That's independent. And in a table, we usually write that one first and then dependent afterwards. Okay. Now we're going to graph it. To graph a relation, make the independent variable the horizontal. I'm going to underline that. Make independent variable horizontal and the dependent vertical. So how do we graph this? We have our table. I'm going to copy it down again. So hours worked. And that corresponds to money made. So same table as before. Okay. Now I'm going to draw a kind of a box. And it says I want to make my independent horizontal. So that's the straight across left right line. So that's my hours worked down here. And then the vertical up down line is going to be our dependent variable, which is the money made. So now we're going to put the numbers for our dependent variable along the bottom. So hours worked should go from 1 to 8 because that's what's in my table. And there's no real reason for us to go past that because in this scenario, it said it was a maximum. So follow along with me. Practice making this table, please. Or this graph, rather. And you know what? It's okay to eyeball it like we did. We're not really measuring it with a ruler and making sure it's picture perfect, but try to make the spaces the same. And if they're a little bit off, that's okay. Now, our money made is supposed to go up to 96. So I'm not going to draw a little dash mark to go all the way to 96, having like 96 different dashes and entries. So instead, I think I'm going to go 100. I'm going to round up to a nice, easier number to graph, like 100. And then we're going to cut that in half at 50. And then from 0 to 50 and 50 to 100, that's a little easier for me to break into groups of 5 maybe. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So each one of my dashes will be 10. And now we can, one entry at a time, find where those live on the graph and see if we can connect them. So for 1 hour worked, it should be up to 12 on money made. So over 1 up to 12, that's about right here. 2 hours worked should go up to 24 for money made. 336. 448, and just down the line. So notice it's not precise. So technically, this is a sketch of a graph because I didn't measure my sides, my hours worked, and my money made. And so we're kind of just eyeballing it to get an idea of what this looks like. 5 hours and 60. But notice that my dots that I'm graphing kind of look like they're in a straight line. Six and 72. Any questions so far on this graph, please?
No, I'm pretty good.
Okay, thank you. Let me know. If anyone does have a question, let me know. So we graphed these out. They do look like they're in a straight line, and I want to point something out to you. Back at the table where I was getting this information from how to graph it, the numbers that I needed to graph it, you might notice that the dependent side, the money made side, well, those are going up by the same amount each time. Plus 12, plus 12. And that's in fact how we found it in the first place, right? Like we realized, okay, she's making $12 an hour. So it's going up 12 each time. And because these are moving up by the same amount every time, plus 12, then we say that this is a constant rate. Because it's not changing. It's always going up by 12. It's constant. It's not like varying into like plus 15 and minus 2 and plus 17. It's the same thing. You can count on it. Plus 12, plus 12, plus 12. And that's why these points that we're making come out to a straight line. Later, we'll look at some where that's not constant. For now, we are going to stick with mostly constant ones like this. Oops. Okay. Any questions? No? I'm going to move on. Let's try some more. Okay, now we're going to talk about domain and range. Domain and range of a relation. Domain of a relation is the set of all of the independent variables. It's the set. It's like a collection of all the independent variables. And range of a relation is the set of all the dependent variables. Remember, independent is what happens first, and the dependent ones happen afterwards. So, assuming that, to go back to Brianna, assuming that she only works like for exactly whole hours, like this. She works 1 hour, or 2 hours, or 3 hours, but she doesn't work for 2.5. She doesn't work for 2 hours and 50 minutes. She only works for full hours like this. Then the domain would be this list of numbers. It's got to be either 1, 2, 3, 4, 5, 6, 7, or 8. So here's the domain for the Brianna example. And the range is the list of numbers that corresponds to all these domain numbers. So it's all the dependent variables that we found. And that was 12, 24, 36, and so on. So we kind of already had these numbers, right, in a table form. But sometimes you're going to be asked to list off the domain or list off the range. And all we mean by that is it's a list of all the independent variables and a list of all the dependent variables. The actual numbers that we have for those. So domain, think independent variables. Range, think dependent variables. Okay, I'll wait 10 more seconds if people are still writing. And then I want to look at some different examples to identify domain and range, identify independent and dependent variables, and do some more graphing. Okay, and we already listed the domain and range of Brianna's relation. Okay, let's look at a different example. And here we're being given a graph. A couple questions on the left. I want to identify what is the independent variable, what is the dependent variable, and then this analysis question. The more tomatoes purchased, what happens to the total price? So let's check out our graph and see if we can figure these out. So it's already been graphed for us. We have tomatoes purchased along the bottom. We have total price going vertically. And then we see a red line that's modeling that relationship, that relation between the purchase and the price. So can anyone tell me, out of these two variables, tomatoes purchased, total price, which one is our independent variable? Can we tell based on just on the picture which one is independent and which one's dependent? Any thoughts?
Tomatoes.
Yes, I think I heard that. You said tomatoes purchased is the which one?
Independent.
Very good. And how did you know that?
Um, well, because in the last problem, the money was the dependent.
Good. Yes. And that's similar to this one, huh? The money is still the dependent. Good. In a lot of our problems that we use math to model, the money we make or um, the money we make is usually going to be the dependent variable. Maybe not always, but almost all the time. Very good. Also, folks, I want you to remember the independent one is always the one we do horizontally. I'm going to write that down here. Independent. And then our dependent is the one we put vertically up and down on the side. Dependent. So that means the total price is dependent. Thanks, Anaya. Good job. Thank you. Okay, now this might be kind of tricky, but it's probably easier than you think. This analysis question. The more tomatoes purchased, what happens to the total price? Is it staying the same? Is it going up? Is it going down? That's what I'm asking by that question. So the more tomatoes purchased, that means as we go farther to the right on this picture. So as we move farther to the right, our line is going up, going upwards more and more and more and more. So we could say that the total price is going up also as as we buy more tomatoes, then the price is increasing. So as we buy more, the price is increasing. And how do we know that? Because the graph is going up as we move to the right. Okay. Let's look at number 3. So we have another scenario. If you want to take a picture of this instead of writing it all down, that's okay. But then I want you to try making a graph with me. So here's our scenario. Tom is parking his car in a parking lot near the supermarket. He learns that the cost of parking is $2 per hour for the first 4 hours. After 4 hours, a maximum fee is reached and the parking charge remains constant. Okay, now this time it's a little different because it says for the first 4 hours, we have this rule, $2 per hour, but then after 4 hours, the parking remains constant, meaning it's not going to go up anymore or down, it stays flat. So let's try making a table for this first, and then we'll use our table to make a graph. Now, the problem doesn't tell us which one is our independent, which one is our dependent. But like Anaya pointed out for the last example, the cost, the money, is almost always our second variable, our dependent. So let's start like that. Hours parked. That sounds like one of our quantities. And the cost of parking is our second variable. So we know that it's $2 per hour up to the first 4 hours. So let's try doing those first 4. Park for 1 hour, that should be $2. 2 hours, $4. Remember, it's $2 for every hour. 3 hours would be $6. and then 4 hours would have us all the way up to $8. So it's $8 to go park for 4 hours. Then after 4 hours, the parking charge remains constant, which means it's not going to change anymore. So how do we show that with our table? 5 hours? Still $8. 6 hours, still $8. Oops. 7, still $8. So let's try to model this scenario with our graph now. Make your box. We've already picked hours to be our independent, so that goes along the bottom. Hours parked. And then on the side, going up and down, is cost of parking. Okay, this time our numbers aren't as big as the last example, so it'll be a little easier to graph it. We want our hours parked to go from a 1 to 7 at least, because that's what we wrote out. So we're just going to start here. 1, 2, 3. All right, and then we want our cost of parking to go from 2 all the way up to 8, and it doesn't even need to go higher than 8 because all the numbers that come next in our table, if we kept making more, would all be 8. So let's try that. Okay, so 1 to 2, 1 hour, $2. So I'm going over to 1 on my hours parked and up to 2 from there to represent that $2 that it cost. Then for my next entry, 2 hours, $4. So that's over to 2 and up to 4. 3 to 6, 3 hours, $6. All right, and then 4 to 8. And then from there, 5 is also 8 high for the cost. 6 goes to 8 and 7 goes to 8. So that all the rest are going to look like this. Over to 5, but still up to 8. It's a straight line across. And if we connect these, then our graph could look like this. So,
If I have a question.
yes, go for it, please.
So for 4, 5, 6
Mhm.
on the other table,
Mhm.
why is it saying 8 for all 3?
Yeah, that's a good question. Because in this story, in this scenario, they're giving us some extra weird information. Let's look back at the top again. The cost of parking is $2 per hour for the first 4 hours. Okay. But then it says after 4 hours, a maximum fee is reached and the parking charge remains constant. So because of that, it's telling us that after that 4th hour, so for the 5th one and the 6th one and the 7th hour or more, it doesn't keep increasing $2 per hour. It stops and stays flat at 8.
Oh, okay. So it continues just to be $8.
It continues,
after
correct. Yes, yes.
Okay, cool.
Now, if it hadn't said that, Tira, we wouldn't have done that. If it hadn't said the parking charge remains constant after 4 hours, then I would have just kept going up by 2 hours every hour. But they threw in that extra little thing. And so that's how we modeled it with our table and then with our graph. Any other questions or concerns so far, please?
Yes. So
Yeah.
with the table, I understand that we went to 8, but if we wanted to, could we have kept going?
Of course, yes. Correct. So there's no reason that I stopped here except that I ran out of room, and I wanted to demonstrate a few terms of it staying at 8, to just like what you pointed out.
Okay, cool.
Totally. So we could though have gone forward and done 8 and 8, 9 and 8, 10 and 8, and it would kind of continue forever. And you know what, Tira? We model that with the graph with this arrow. So because I put the arrow on my line, that's kind of a visual clue that this line goes on forever. That's what we mean by that with the little arrow. Even though we don't think about it, we don't think about it explicitly. But that's what your mind knows when you see that. It means, okay, this line he made is going to keep going forever. Like 8 and to 9 and 10 and 4 and even farther.
Okay.
Does that
cool.
answer or not really?
Yeah, it does.
Okay.
Thanks.
Thanks. Good question. Thank you. Anyone else? Any other questions? Anybody? Okay. I think I've got a couple more graph questions to look at with you, and then we want to talk about continuous and discrete. Okay. Here's another example. Again, please feel free to take a picture of the writing so you don't have to write down the whole word problem. But then please do try to model a table and a graph with me. A 500-gallon water tank drains, seems important, 500 gallons, drains, that means gets smaller and smaller, right? It's at a rate of 50 gallons per minute. The amount of water left in the tank, depends on the number of minutes it has been draining. Dependent. The amount of water left in the tank is dependent on the number of minutes it has been draining. They're kind of telling us a clue this time, an independent and a dependent variable. Make a graph of this relation and identify the domain and the range. Okay, so let's start by figuring out what's independent and dependent. Let's try to make a table, and then we'll use our table to make our graph. They're telling us in the second sentence right here, amount of water depends on number of minutes. Are those both numbers? They are. Amount of water we're going to measure in gallons. So that's numbers. And the number of minutes is obviously numbers as well. So because those are both numbers, we can model them with math and a table. So amount of water is our dependent. Independent first will be number of minutes. So I'm going to just say minutes for our table, and then amount of water. Number of minutes draining. So let's start like this. I'm going to put a 1 here. 1 minute drained, 2 minutes drained, 3 minutes drained. And then we'll try to figure out how much water is left in the tank after all these minutes. And here's something else that's not very obvious, but I'm going to actually, on my table, put a 0 minutes draining. 0 minutes draining means right before it started, right? When the tank is full. So this will help us put the whole table together if we can start it at 0 this time, because we're tracking minutes after it's been draining. So this way we can show how much there is when it's full. which is 500. It told us that in the beginning. It's a 500-gallon water tank. I guess we're assuming it's full at 500, but I think we are. And that'll help us see the ones that come next. So after it's been draining for 1 minute, it's lost 50 gallons. So it's at 450. 2 minutes, it's lost another 50. Remember, it's draining, so it's losing 50 every minute. 400. And it goes down by 50 again. 350. And then 300. And we'll do a few more here. Let's do 5 and 6. $250 and $200. Okay, so this is the first example where our numbers, our dependent variables going down, decreasing. So start the same way as normal. We know our independent is minutes. Draining, and our dependent is amount of water left in tank. Now look at your numbers. Look at the collection that we made in our table. That's kind of like our domain and range already laid out for us. Remember, the domain is the set of numbers for the dependent, for the independent, and then the range is the set of numbers for the dependent. So let's label that here. Domain and range. We just want to make sure that on our graph, we have space for the numbers that we're going to be using. So along the bottom, it starts at 0, which is right where the two lines meet. There's our 0. And then we're going to continue like normal, 1 up through 6. And just do your best to make them close to the same distance apart, but doesn't have to be perfect. Because we're just making a sketch. All right, and now we know that this has to start at 500 high. So I'm just going to go as high as I can on my page and make it 500. And let's cut that in half. 250. And if we wanted to make each of these 50s, then I think we're cutting in those into groups of 5. So then try to make it a group of 5 like this. 50, 100, 150, 200, and so forth. Okay, now we can graph the different data points that we have from our table. So at 0 minutes, it should be up at 500. Right here. 1 450. 2 400. 3 350. And you can kind of start to see a straight line forming. 4 to 300. And don't be hard on yourself if it doesn't look exactly like mine. It's okay. I want you to just get your practice making a graph today. 5 and 250. And see, it's pretty good. It looks kind of like a straight line. And it should because it was a constant rate. It's going down 50 every time. Even if we didn't think about that earlier explicitly, we knew it because that's how we were figuring out each next number in the range. Okay. Now the domain here, technically, the way we wrote it in our table, it's the numbers 0, 1, 2, 3, 4, 5, 6. The range would be 500, 450, 400. But let me ask you, when the tank is emptying water out, is it jumping down from like 500 gallons and then all of a sudden 450 and then all of a sudden 400? No, right? It's like a continuous stream and it's losing like 1 ounce at a time or 1 drop at a time really fast. So technically, even though we figured out just these points, right? We figured out the minutes and how much water at that minute. It's really going constantly. It's going continuously. And so for instance, like this point right here, whatever that is, that's a legitimate amount of time. Looks like it's about 1.5, maybe a little more than 1.5. And how many gallons does that look like it is? Maybe it's 420 or 425 or something. And of course, there is a point that exists when it's been 1.5 minutes and that many gallons correspond. So my point is that even though we figured it out using domain and range of like whole numbers, there's all sorts of decimal numbers and fractions that exist along our line for this example. So the domain isn't just the numbers 0, 1, 2, 3, 4, 5, 6. When you think about it, the domain is really all numbers greater than 0. You can't have negative minutes, but starting from 0 going onward, we have all those different entries, like 0.5 and 0.75 and 1.5, all the different fractions and decimals that live on this straight line we made. And then our range, remember, this is the set of numbers that are in the dependent variables. So notice that for range this time, it starts off at 500. And then it just goes down, 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 down. So for our range, it's all numbers less than or equal to 500. Sometimes domain and range is a straight up list of numbers. And sometimes we're going to describe it like all the numbers bigger than this and all the numbers less than this. And it depends on the story and what we're measuring, like minutes, dollars, water in ounces or gallons. It depends on the story to kind of tell us if it's a list of numbers or if it's a description like this one was. Okay, if you haven't copied this down, take a picture quick. We're going to move on. And it looks like we're almost done with class. So let's see if we can do a little more here. I'm going to skip number 5. I want to talk about real quick continuous versus discrete. So I actually started talking about this just a moment ago without using that language. A relation is discrete if it only includes single points. And these would be graphed with points and dots only. And we can compare that to a continuous relation if it includes all the points infinitely, like a straight line. These are graphed with lines. So to compare them with pictures in their graphs, discrete would be just like 1 point at a time. where continuous would be a straight line. So that last example with the water coming out of the tank, that's an example of a continuous relation. Now, Brianna, working as a babysitter, we graphed it as just points, single points. But it just depends on the scenario. If she only works 1 hour at a time and nothing else, then it would be a discrete for Brianna. But if she does work like 2.5 hours or 2 hours and 15 minutes, then that's continuous. So to know if it's discrete or continuous, ask yourself, can the variables be just whole numbers? And that's discrete. Just whole numbers. Or can it be all the numbers in between the whole numbers, like 1.5 or 1 3/4? And really quick, let's just do some comparisons to think about discrete versus continuous variables. And I'll wait 10 seconds if people are still writing. And then I guess we'll stop for the day after this. And don't go yet because I need to see your notes to check you off for participation on this today. Okay, so let's do this quick activity. Determine which of these are discrete or continuous. Now, the question is, are they measured only in whole numbers? Or is it more like the water draining out of the tank, where it's not measured in whole numbers, it is constantly, continuously dumping out water? So, the population of dogs in a village, would this be discrete or continuous? Can you have portions of dogs in a village or only whole numbers of dogs in a village? Anyone have an idea on this one? No? Okay. Well,
Oh,
yeah, go ahead, Levi.
I was gonna say you can only have whole numbers.
You can only have whole numbers. Thank you so much for jumping in. So that's the easier way to ask the question, right? Can you only have whole numbers or can it be all the fractions in between the whole numbers? Fractions means continuous. Discrete means whole numbers only. So the dogs in the village would have to be discrete. We'd measure them as 1, 2, 3, 4, not portions of dogs, right? The distance covered by a train, distance. So a train leaves the station and it's going across the land. It doesn't jump ahead 1 mile at a time, right? Or 1 foot at a time. That would be a nightmare. It's continuously moving. It does every inch at a time, every little millimeter at a time. So distance covered by a train.
So it's continuous.
Continuous. Thank you. Yes, absolutely. Number of books shelved in the fiction section of a library. Thoughts? Anyone have an idea on this one? Was someone answering? I'm sorry. Maybe not. Maybe I thought my connection cut out. Number of books, we only measure that in whole numbers, right? So that means this is discrete. And then this is weird. That's not supposed to be there. The number of bracelets sold at a store, also discrete.
Yesterday, my husband was laughing at me because I answered, and he just didn't say anything, and he ended the Zoom.
So basically, discrete means that it's not something that can be continued.
Correct. Yeah. It would only be measured in whole numbers.
Okay.
So today was heavy in vocabulary. Thank you to everyone for coming and for following along and trying. If you could really quick, just turn on your cameras and I'm going to check you off for taking notes if you have them.